Welcome to the class of Principle of Communications. In this video, we are going to go through some concepts of carrier recovery. Mathematically, we have a signal xt multiplied by e to the power j 2 pi fct. That is the upconversion step. And then at the receiver side, we receive a signal rt. Suppose it's ideal, st times e to the j 2 pi fct. We will multiply by e to the power negative j 2 pi fct. That is the down conversion back to DC. So ideal case is back to ST. Now the carrier is FC here. For carrier recovery, when we are dealing with a practical system, the transmitted signal will be j 2 pi fct, but with an arbitrary phase, phi. This phase can be caused by some delay of the device, transmitted delay of device of the receiver side, and also the delay of propagation through the media. And then at the receiver side, we multiplied by e to the negative j 2 pi fct. However, at the receiver side, my carrier is not precisely the carrier at the frequency, so we call it fc prime. Therefore, the signal will be st times e to the j 2 pi fc subtract fc prime t plus phi. Okay, so there are two things give us ambiguity. One is we have this j 2 pi delta fct, where delta fc is fc subtract fc prime. That's the carrier phase offset. The second part is e to the j 2 pi e to the j phi, which is due to the phase term. So that is the carrier phase offset. If both of these are non-zero, then at the receiver side, I either need to find the delta fc, or find a way to compensate these two non-zero values in order to recover a perfect st, the received signal. Again, phi is due to the delay, propagation delay, the delay of devices at transmitter and the receiver. There is always a non-zero number, and I always need to find a non-zero phi at the receiver side, or compensate that. Delta fc, it's most likely that a crystal oscillator at transmitter and the receiver, they are different. So there is always non-zero delta fc, so I also need to find that. In the following examples, in practice, instead of using an exponential, we would like to using a cosine function for upconversion and downconversion, because everything is real. So it's cosine 2 pi fct plus phi, which is the same as st times a half of e to the positive j 2 pi fct plus phi plus half e to the power negative j 2 pi fct plus phi. Okay, so in practice, we're always using cosine, and that is what we are going to use in the following examples. Here is a generic block diagram of a communication transmitter and receiver pair. At the transmitter side, we have signal ST, which is signal after digital modulation post-shaping filter. We will upconvert that onto a carrier frequency with carrier frequency FC and a phase phi. The signal will be given by ST times cosine 2 pi fct plus phi. The signal goes through the channel and received at the receiver side as a signal RT. Suppose the channel is ideal. There is unit channel gain and no interference. Therefore, RT is equal to this transmitted signal. Then the receiver side, we will do down conversion. Usually there are two steps: analog down conversion and digital down conversion. Analog down conversion can use some inexpensive analog devices to down convert the carrier signal down to intermediate frequency. And then we sample that as a digital signal using digital downconversion, downconvert the signal to DC. Here, let's treat the receiver downconversion site as one block. So here, everything is a downconverter. At the downconversion part, what we want to do is I want to recover the transmitted signal ST. So ideally, what I can do is RT multiplied by cosine 2 pi FCT. That's downconversion. And then we doing a low-pass filter and keep the DC part, filter out the high-frequency part at 2FC. And of course, the problem here is that I also need to know the phase phi, as well as the carrier frequency used as the transmitter. So for a practical receiver, there are two major problems. I need to recover the carrier phase, which go through the channel that they can change because there is a propagation delay. The other problem is I want to recover the carrier. Now, in reality, the crystal at the receiver and the crystal at the transmitter, they are not the same. So there is always a frequency drift. So I want to make sure that I can catch the exact FC in order to do this downconversion. Carrier phase difference is due to the propagation delay and the phase delay of different devices at the transmitter and the receiver. So we need to recover that. If the carrier phase changes, we also need to do carrier phase tracking. Now, carrier frequency offset is due to the difference between the crystal oscillators at the transmitter and receiver. And we can treat that also as a phase change because basically it's a changing phase of FCT. We can do a phase tracking onto the carrier offset. We will see later on. We may not be using the existing carrier recovery technique on that. Maybe need to add something more. So here, let's first, suppose I, at the receiver side, know exactly the carrier frequency FC, but somehow I need to calculate the carrier phase phi. My received signal, RT equal to ST times cosine 2 pi FCT plus phi. For modulation, if I'm using a large carrier modulation in the amplitude modulation realm, this is I am adding a 1. I'm adding a pure cosine function onto my message signal. And then this is the modulated signal. So we have here is a ST cosine of 2 pi FCT plus phi plus a pure cosine function. And previously we said this cosine function is a large pilot sine wave, pure sine wave. Maybe I can catch the carrier, maybe I catch the phase from this signal here. Let's do Fourier transform on received signal RT. So the Fourier transform here is R of F is equal to the Fourier transform on the first part, ST cosine 2 pi FCT plus phi, and the Fourier transform on a pure cosine function, 2 pi FCT plus phi. And this gives us the first term is capital S F subtract FC. Because I have this phrase term, we need to put a e to the positive j phi here. This is coming from when I using the Euler identity to write out cosine as a e to the positive j, the entire thing, plus e to the negative j, the entire phase term here. So here's everything is a half, plus half of e to the negative j phi s f plus fc. Then for the second term, doing a Fourier transform, we have half. Similarly, we got e to the positive j phi delta f subtract fc plus half of e to the power negative j phi delta f plus fc. Now, if my signal at the frequency f subtracted fc, if this term is much larger than the signal due to my message s, then I can focus on this term around carrier frequency fc, and using that to calculate the phase theta. Let's look at a MATLAB example on calculating phase phi from the received signal. So here I have the signal is PAM, pulse amplitude modulated, using 4 different levels: -3, -1, +1, and +3. So here the code here is just we have a length of n, 4 levels, variance of 5. So roughly speaking, if you get a -3, -1, +1, +3, roughly speaking, you have a variance of 5 of different symbols. And then we know MUP is the oversampling by integer of m. M is 20 oversample rate. PS is post-shaping filter. We're just using a Hamming window to do that. So S is a filter the signal. That's filter PS with the MUP, the signal that is oversampled. We choose carrier frequency 1000 Hertz, and we put the phase offset -1. Then we construct the carrier. Now in this case, the carrier using the carrier frequency known, but it has a carrier phase offset, which is -1. We modulate it if we are doing a suppressed carrier, so it's simply using my signal S multiplied by the carrier. If I'm doing a large carrier, so we have a S plus 1 times the carrier C. So we have 2 different received signal. Suppose we are using 2 different modulation methods. So we will going through that and see what we get in the frequency domain. Running the program, and let's check with the Fourier transform of the large carrier modulation. So FFT RLC. Let's plot that. Figure 1. I'm on here. I'm going to plot ABS, absolute value of FFT RLC. So here's what we get, the frequency domain signal, which we do have, it's cosine function, so we have both on the positive frequency and negative frequency, they are even symmetric. We do have a very strong carrier. Because it's a large carrier, we're adding 1 onto my message signal. So here's my signal at a positive FC, another signal at negative FC. Now in this program, what we do is we are finding what's the maximum. So line 16 is to finding the maximum of my spectrum and also give the index of this maximum. Line 17 is just calculate the frequency vector to make sense all these index and map onto a frequency of unit hertz. So it's a length of from 0 to length of t over ts, which is sample period. So each step will be a sample frequency from 1 to a consecutive 1. And then time the length of t, that's the entire span from 0 to the length of t. Therefore, we got our frequency vector. Then we checked on the frequency vector, where is the value of this position of I max, and that will be the frequency that has the largest frequency value. So we have already given that out. Frequency L, that is 1000. That's FC. We just find that on my frequency domain picture here. This point, the second peak corresponding to 1000 Hertz. We also find at this point, at this frequency point, which is I max, that's the index, what is the angle or the phase of that point. So we plot out phase L. That gives me the phase phi. But we can see here, it's far from correct, because we are trying to find this phi using this term. But at frequency Fc, F equal to Fc, we also have this term. It can be small, but it has some effect. So it's not exact. I'm not calculating a very precise phi. So this method is just a rough way to showing that if the carrier can be relatively large, we can get a sense of that, but it's not precise. We will see later on how we can find this. Now the second part of the receiver is to receive the signal that is using the suppressed carrier modulation. So that's FFT RSC. We plot out figure 2, plot ABS of FFT RSC. So here's what we get. That's the suppressed carrier modulation. Yes, we do have two peaks around frequency 1000 Hz and negative 1000 Hz, but we do not have a very large pure sine wave. Therefore, if I'm using the method finding what's the position of the highest peak, you'll find out here it's not exactly on 1000. It can be some off because everything here is due to the signal ST in frequency, that's capital SF. So that will give me some errors if I'm trying to find the maximum. So this is what I do on line 22. I'm still using the old technique, trying to find the maximum on the spectrum, and at this maximum position to find the frequency and to find the phase. So we'll find out the frequency of S. That will give me not exactly 1000. It's actually 1091. It's a little off. Also the phase, and we know at this time when we find the phase of phi, it cannot be trusted because it's just simply off. It's not on the frequency of 1000. In the suppressed carrier modulation case, what we can do is we can use a squaring process to help to receive the signal, to help to find the carrier phi. So the square on the received signal RT, it becomes ST squared plus cosine squared 2 pi FCT plus phi, and that equals to half of ST squared cosine 4 pi FCT plus 2 phi. So here we have a ST squared. Now this is a positive signal, so it will have a less variation. In a sense, it has a very less variation. So suppose this is a real number. If it's not, we use the absolute value squared. Suppose that's a real number. So we indicated that by a average of the square plus a variation called a VT. We understand that this VT has a much less variation than the received signal RT because VT is positive. Okay, and then we have this immediate term. It stands out quite like what we have before. That's a 1 plus S. 1 will be standing out. So if we are doing this, the signal becomes half of S average, which is a constant, times cosine 4 pi FCT plus 2 phi plus half of VT, which is relatively small compared with S average, cosine 4 pi FCT plus 2 phi. Oh, we have a plus 1 term here. Sorry about that. We got a plus 1 term here. So there's another 2 terms here. We have a half of S average square plus half of VT. Now, at this time, if the first term is quite large, as I said, this term is usually much larger than this positive value of ET, and then it will stand out as a pure sine wave. It's just one spike on the frequency spectrum again. If we can find that, we find where is the maximum frequency, where is this position, and at that time we will find the phase, which is 2 phi. And using that, we can have an approximate feeling about what this phi should be. Now let's continue with the MATLAB example to adding this squaring technique. The received signal is the suppressed carrier RSC, suppressed carrier modulation. Q is the squaring, nonlinearity device. So let's plot out, first plot out the function q, and we can see here's the function q. Q is squared, so everything is positive. If we zoom in here, so everything is positive. It's just positive signal. It's positive received signal r squared. And then we have this is a filter. This filter is give me the filter which is around frequency 2fc. But first, let's look at what is plot of ABS FFT of Q. What is the spectrum of signal Q? We can see this. We got a few spikes. Those few spikes are according to very strong cosine signals, actually at 2fc and at fc, etc. And the signal st of Q becomes quite small. Okay, compare with the signal capital R, capital Q. The frequency spectrum of the squared signal, it becomes quite a large of those cosine functions. And then after this filter around 2fc, let's see, we plot out ABS FFT RP. So we got two very nice spikes at 2fc and a negative 2fc. Okay, this is our actual signal FFTR BPM go through a bandpass filter. The bandpass filter has a passband around 2fc. And then we are using same method, line 11, to find the maximum of this spectrum, find the position corresponding to this maximum value, and to map with the frequency vector to see what is this maximum frequency. So frequency S, the maximum peak, the positive peak is at 2000 Hertz. Exactly, that's what we have at 2fc. And then this phase P is equal to that, negative 0.74. Now, if we compare with previously, we have, let's see if I still have that. Let me run that again. The previous functions here. We have this phase phi, which is negative 0.37. And we just find out using our squaring technique, the phase becomes negative 0.74, which is 2 phi, Even though it's not precise, but we understand that using this squaring technique, we exactly get the phase is around 2fc and with the phase term of 2 phi.